We're starting 7 seconds late. Oh gosh, we're on a little bit of spillage here. Oh well, yeah, I'm sure it'll be okay. Well, thank you for coming to this talk on G1GC. I think I see a couple of people in the audience that actually don't need a lesson on G1, so we'll try to ignore them for the rest of the session. For the others, let's have it's a small group, which is really good. That means we can get kind of personal about it. So what makes you interested in this particular talk here? So in other words, I guess more specifically, who's trying to tune garbage collectors right now?
Try to. Don't need to.
Out. Yes. Yeah, he doesn't need to because he's not using Java. Okay. So yeah, exactly. So no one's trying to tune garbage collectors or anything. So yeah. In the past, yes. And okay. Does anyone even actually know what garbage collector they're using? Okay, how's that? Yeah, sorry. I tapped it before. I thought I heard a tap. Okay. Blah. Test failed. I didn't turn red. Okay. Right. Okay. So now we're basically in this condition here, and so what happens is that we're going to start allocating again. Now instead of coming from this cartoon version of a heap, I'm going to switch to a drawing that we've done based on what heap really looks like. Okay, and this is what it actually looks like this is taken from a live application. So we've mapped the data out in an application right here. So you can see now we have the young filling up again. We have the two spaces happening. And what the two spaces do, just what they did in the generational collectors, we're going to go basically copying to two space until we hit something called a tenuring threshold. The tenuring threshold by default is 8 or 15, depending upon conditions. And at that point, the data will be promoted into this area called tenured. So if this all looks familiar, it's pretty much, as you've seen before with generational collectors. Not much difference. So, let's go back and revisit this mark sweep phase, right? Now, there's one step in here we sort of glossed over, and that's calculate a root set for the CSET. So if we go back to our particular diagram here, what we're going to see is like, okay, so where do the GC roots live for these regions down here? And the answer is they live up here, as well as all of the other places we expected, like stack frames, code frames, things like that, right? So now we have a problem, right? We have a time complexity issue with doing the scan for roots. In order to find the roots, we have to scan all of tenured. And we don't really want to do that. So how are we going to manage that? Right? Because scan for roots is going to be linear to the size of heap, and that's why we didn't want to use CMS. Because scan for roots was linear with the size of heap. So there's some work we can do here. And this gets into the what I would call the difference between, a balance of work between the allocators and the collectors that I mentioned before, right? And in this case, it's like a pay me now or pay me later scenario. And so what we can do is we can give a lot of work to the allocators, like we do in C++, right? Where there is no garbage collection, pretty much. Or we can give all of the work to the garbage collector and not have the allocators help out. Or we can balance the work between the allocators and the garbage collector. And so in this case, what we want to do is we want to introduce another data structure, which we're going to call a remembered set. And what the remembered set is going to do is balance the work. Oh, hello? Oh, it's on again? Okay, fantastic. Okay. Right. So what we want to... working. Okay, try again. Okay, so we'll have to do a remark, and this is to reconcile the changes that happen in HEAP between the initial mark and and what it is that you actually need to tune. How's that? Whoa. Whoa. Now you can hear me without shouting. Oh. You can hear in the back there, Michael?
Yeah.
Awesome. Okay.
Kirk,
Yes, sir.
what is the default region size?
It depends on the max heap size. So it's calculated off of max heap size. But it'll be either 1, 2, 4, 8, 16, or 32 megs, right? And the target number of regions is 2,048. And what I would say is that you don't really want to skimp on that. The more regions, the better. Okay. So how do we get a GC log? Well, in JDK 8 and below, you use these ones. In JDK 9, we have unified logging, and I think I've selected the slide deck that doesn't have those settings in here. Sorry. They'll be posted, so you can see what's happening in JDK 9. Okay, so this is a bunch of information that I find that's what I call a good core level setting, so you can get enough information so you can really figure out what's going on. Now you're going to get this very, 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 very large log, which is neither human nor machine readable. It's lovely. Okay, so what do you do with that? Well, if you don't like reading them, then we have some tooling that can actually help here. So I would suggest that we take a look at a GC log using Sensum. So I'm just going to switch over here, use my fancy mic holder, and hopefully you can still hear. Maybe I should sit for this whole thing too. Okay. Ba 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 ba. Oh, what do you see down? What's that? This is one of the beaches that we visit for our unconference in Crete. Oh. So J Crete. So we'll put a plug in there for J Crete. Okay, so let's start up. Let's go to a conference to advertise another conference. How's that? Okay. Okay, so I was doing some testing here before. Let me pull out downloads. I'll try this one. So I'm just randomly, I got some logs in today, so I haven't seen them yet. So I'm just going to randomly see if there's anything interesting to see in it. But it doesn't matter. I'll give you an idea what's going on. So let's put that up over here. Let me bring it up like this. And then I can do that. And hopefully you guys can have a fighting chance in the back of seeing it. Everybody happy with that? Whoops. Yeah. Okay, so let me pull this over here so you can actually see. Okay, so what we're going to do is use the tooling here to, this is an older version, so I haven't updated. Anyways, long story. So we have a number of different analytics and stuff like that we can actually look at the heap to try to go through and find things that can help you understand what's going on. So here we see that there's an analytic lit up here, which means that we have a 35-second pause time in this particular application. Actually, I better make sure this is a G1 log first. Yes, awesome. It's a G1 log. So that's good. Yeah, I collect GC logs as a hobby. I have probably the largest collection in the world. If you, I collect them. Yeah, and I garbage collect them. So so if you want to send more, it's okay. So we've actually tuned about 3,000 JVMs this year for garbage collection, as an idea. Okay. Blah blah blah. Okay, so there's all kinds of other things here. So you can look at the mixed collection distribution. I like to see this flat because that means the work has been evenly distributed. Okay, and in this case you can see that there's a bulge here towards 2 and 3 mixed collections. I'd like to see it like flat all the way up to 8, if I can, right? Because that means that everybody's doing a little bit as opposed to having somebody do a lot, and that generally gives you a better pause time picture. And we can look at the pause time picture here, so that's really a pause time problem. But we can come down here and say, okay, so let's look at the standard views. Heap usage after collection. We seem to have a problem here. I think I can explain this right now, but let's wait for a second. So we have HEAP tenured after collection. So these are the occupancies of the HEAP after the collection. Oh, sorry, just tenured. I haven't factored out reserved here, so this is lying to you. But this is a close enough approximation here. And the red bar actually represents the size of the pool. Okay? If we go down to here, we can see each of the major categories of phases within the G1 collection, right? And you can see, if we look at this as a phase percent, we can see that pretty much the parallel phase is dominating. Okay? But the other phase, whatever that is, other phases are doing a lot of work here also. So what I want to do is I want to go to other phases and see what the other phases are. And you can see there's this yellow stuff up here that's happening a lot. And that represents reference processing. And that's dominating the other phase. So one of the things I'd go back and ask, okay, do you have parallel reference processing turned on? Because it's not on by default. Okay? And that might help calm this area down. Back to the parallel phases, you can see that, what are we looking at here? There's a lot of object copy is a dominating cost. And that's normal, and it should dominate. If it doesn't, then you have some other issues. Okay? Maybe you have RSET scanning and updating is a problem. And if RSET scanning and updating is a problem, that means your RSET refinement is not aggressive enough. You might want to tune that. Okay? Here is some information about safe pointing. Of course, that's the thing that creates the stop the world pause. In this case, it's, oops, mostly okay. Move this over here to create a problem. We have a CPU summary. And this is, you know, if you look at this, right, you can see, okay, how much parallelism are we getting? Are we getting good parallelism? Is the kernel interfering with the garbage collection process? Things like that can help us understand if the garbage collector is the problem or if there's something in the environment that's the problem. Of course, here's our reference processing. And if we want to look at, okay, what's taking the reference time, it's these guys over here. And those are weak references. Not unexpected. GC cause. You know, humongous allocations that are responsible for about 60 some odd collections. You know, so there is some sort of issue here with humongous allocations that could probably calm down to make the whole thing a little simpler. But you know, in reality, when you look at the whole thing, we have really, that's the problem, right? And it took a full GC to clear the thing out. Whatever the issue was, it required a full GC. Now, we've been seeing this in applications for quite some time. And it's taken quite some time for me to actually figure out what's going on. But to me, I think it's pretty clear now. What's happening is that it's how the humongous allocations are actually being managed by the garbage collector. So if you have a humongous region, it's actually not being marked in all cases, which means the weak references are not being declared dead. And so since they're not being declared dead, you hit some thresholds, and all of a sudden the weak reference allocations with the data that they're holding on to will just go like bang. You get a full GC, clears it out, bang, and we're done. Okay, so seems to be some, and I don't know the full answer to this yet because we're still sorting it out, but there seems to be some interesting interaction between the weak references in large buffers that is aggravating the garbage collector when they become humongous allocations. Yes?
Do you have some examples of typical users of peak references in libraries or?
Caches, hibernate caches, any type of cache like that. Yeah, that would be a typical usage. I was working on a simulation on the flight here. So I got the behavior. I don't have churn. I need churn in order to be able to prove. Once we prove, then I can go back to the JVM guys, the G1 guys, because so far they haven't believed me. They haven't believed me that there's something wrong here. But now that I have a bench that's close to proving it, they're going to have to explain what's happening in the bench. Okay? Anyways, so in this case, we had that issue to deal with, and in this case, it might be try to figure out where the humongous allocation is, and try to see if we can eliminate it or buffer it or do something with it, or do something like that with it. Maybe we don't have to use it at all. Okay, sorry. Any questions from that? But anyways, you can see we can use this data with our knowledge how the collector works to decide what to do. Do we need to make the heap spaces bigger? Do we need to work with refinement? Do we need to balance mixed collections? Do we have something else going on outside of the system? Okay? Let's see if we can go back to slides here. Okay. So you remember I said that object copy was the issue, and there's nothing you can do about it? Well, there is sort of something you can do about it. There's nothing you can do about it on an individual collection basis. But overall, there is something you can do about it. And so if you want to control object copy costs, this is sort of like you have to play the long game here. Okay? So how do we do this? Well, you see this yellow curve that we have here, right? That's known as the weak generational hypothesis. And it basically describes the lifespan of data in HEAP. And it comes from the observation that data is either around for a very short period of time or is around for a long time. Okay? And that's what that curve reflects. Now, every time you draw a curve, all of a sudden you can do other things with the curve, right? It's a curve. And one of the things we can do with the curve is we can take the area under a curve. And what does the area under the curve say? Remember back, remember back, remember back. It's volume, right? Volume, of course. So what the curve says is the volume of reachable objects at any point in time is constant for some variable definition of constant. Okay. So in this collector, the advantage of it is like, why do we go through all this trouble of coming up with such a complex collector, right? Well, the cost of a young generational collection in generational collectors is dominated by the number of live objects in most cases. Here, we've moved that property of dominated by the number of live objects into tenured. So the overall cost of a collection is dominated by the number of live objects. And this chart says that's approximately constant. And since we're copying that volume of data, right, on each collection, how do we reduce the overhead? Don't collect as often. Now, in generational collectors, that meant that you ended up with a really long pause. With the G1 collector, as you can see, you don't. So one of the successful tactics that we've been able to employ, and this works really well for batch processes, is simply slow the collector down by making the heap size. You can see, you just make it go from the white line to the red line, but the impact on the pause time should be constant. Should be no impact on the pause time. And we've actually used that technique successfully in a number of different cases to tune the collector. Simon's looking puzzled. Okay.
So all the other can because there is another percent of allocated small clusters are called.
Right.
Also increase this, like I would say, because the assumption is that at the end you don't really use all this
Space.
Yes.
Yeah. Well, the G1 automatically takes more memory than any other collector on the planet, as does the C4. Maybe not as much as the G1, and there's other advantages of using C4, which I won't deny. You know, so I'm not advocating one garbage collector over the other. I'm just saying, you know, this is how this one works. And yeah, I mean, you're going to use a lot more memory with this particular technique. So it's basically a time-space trade-off in that case, right? Something we make all the time. Cool. With that, I think I've just about hit the mark on timing. I got like a minute left. Is there any questions?
This is more of an aside question. In machine learning, now it seems that TensorFlow is like the execution environment.
Right.
We have the GPU, the TPU, or the CPU, and then you have the graph as an abstraction.
Right.
Do we have something similar in the works for the JVM?
For an AI learning, yeah, yeah, there's a number of different AI frameworks you can use for the JVM, and deep learning for J, H2O. So yeah, you can use these ones also, or you can just continue to use TensorFlow if you like, right? Okay, I've run out of time. Thanks for attending. See you guys.